And the third and final speaker of the session, unfortunately, the original speaker couldn't join us in person because of visa issues, but we have like a short-time replacement, which is probably also going to give us a very nice talk. Juepeng, who is an associate professor at the Yat-Sen, I hope I'm probably doing a horrible job in pronouncing it, university in China, and he's also a researcher at the National Supercomputing Center in Shenzhen that we have heard a lot about this week already. And he's working on the area between machine learning and remote sensing and physical modeling and Earth system modeling, and I think the talk will probably cover all of those. Thank you.
Thank you, Peter. Yeah, okay. Hello, everyone. My name is Juepeng Zheng from Yat-Sen University, and I am also a joint researcher in National Supercomputing Center in Shenzhen. And today, I am very honored to present Kai-Shi's recent work and his their group work. And the title is AP3-ESM V2, a hybrid AI physics Earth system model at 1 kilometer resolution on China's new Exa-Scale supercomputers, including 3 Exa-Scale supercomputers. So this work focuses on 3 important directions: high-resolution Earth system modeling, AI for scientific computing, and Exa-Scale high-performance computing. Okay, this photo taken by Artemis 2nd astronauts from the space is the first blue marble image of Earth captured from such a distance from 1972. But our Earth is in crisis from 2023 to 25. Global temperatures passed the 1.5 degree limit for the first time. Extreme weather such as heat waves, typhoons, heavy rains is also getting worse. And so to understand our Earth better, we have to make our model accurate and fast. Our plan is to use high-resolution, AI-driven, and super-fast computing for the next generation of models. So Earth models need a massive computing power because the Earth is very complex. Including the atmosphere, ocean, land, and ice are all connected. At low resolution, small-scale processes like convection, turbulence, and ocean mixing can't be directly resolved. They have to be estimated. But with kilometer-scale resolution, the model can directly simulate more of these processes, which helps predict typhoons, mountain winds, and air-sea interactions. Speed, on the other hand, speed is also key. A model must be accurate and fast to be useful for forecasting. And this needs better models, better algorithms, better system optimizations, and better use of supercomputers. So let's compare AI models and traditional numerical models. Numerical models are physics-driven. They are physically interpretable and more reliable for extreme events. They perform better at predicting record-breaking extremes. But on the other hand, they are computationally expensive and rely on empirical treatments for small-scale processes. Also, AI models are data-driven. They are fast and accurate for short-term forecasts, but they lack physical consistency, struggle with record-breaking extremes, and depend heavily on training data. So we should not treat them as competitors. Instead, we should combine AI models and traditional numerical models. So before introducing our new model, I would like to briefly review our previous work. Our group has been working on kilometer-scale Earth system modeling for many years. we enabled CESM on Sunway supercomputers in 2015. By 2023, a coupled CESM configuration with a 5-kilometer atmosphere and a 3-kilometer ocean could scale to more than 40 million cores and reached over 200 SDPD on New Sunway. In parallel, we have been developing GRIST, a seamless global weather and climate atmospheric model since 2016. In 2024, GRIST achieved about 1 kilometer global simulation on 34 million cores, reaching 181 SDPD. For the ocean component, we have delivered Lycan since the late 1980s. In 2024, Lycan achieved the world's first global ocean simulation with average horizontal resolution better than 1 kilometer, reaching 1.04 SYPD on New Sunway and 1.7 SYPD on Oris. Then, for full coupled model with atmosphere, ocean, ice, and land, AP3-ESM V2, we achieved 1.01 SYPD with a 3-kilometer atmosphere and 2-kilometer ocean configuration on New Sunway. And for the fully coupled 1-kilometer atmosphere and 1-kilometer ocean configuration, version 1 reached 0.54 SYPD on the New Sunway. And our new model, AP3ESM version 2, builds directly on this foundation. So the new model improves version 1 in 3 major directions. First, it increases model fidelity and advances the hybrid AI physics framework. In particular, it introduced multi-component AI integration. The atmosphere includes physics constraint fully AI parameterizations, and the ocean includes an AI enhanced scheme. Second, it improves computational efficiency and performance portability. On the new Exa-Scale supercomputer Lanshan, AP3ESM V2 achieves 1.73 SYPD for the atmospheric model and 3.08 SYPD for the ocean model at global 1-kilometer resolution. And the coupled system is projected to reach 1 SYPD, with about a 3 times performance improvement compared with previous version 1. And third, the coupled 1-kilometer model demonstrates strong capability in simulating important multi-scale Earth system models. So this slide summarizes the overall design of our AP3ESM V2. The first key point is hybrid AI physics modeling. In the atmospheric component, it uses physics constraint fully AI parameterizations. In the ocean component, it uses an AI-enhanced near inertial wave parameterization. These AI components are not simply black box replacements. They are designed with physical constraints so that the model remains stable and physically meaningful. And the second key point is performance optimization. We use OpenMP and Cocos to accelerate compute incentive parts of the model. We also use load balancing, I/O processing, and FP16 mix precision storage to further reduce the cost. And the third key point is portability. Our evaluations are conducted on 3 major supercomputing systems in China. So at 1 kilometer resolution, I/O becomes a major bottleneck. We developed an offline pre-processing tool for NetCFD, CDF, and HDF5 data. The basic idea is to move heavy I/O work out of the runtime critical path. During the first run, the tool generates and catches the partition information. Then for later runs with the same configuration, the model can directly read the cached indices. We call this strategy partition once, but reuse many times. With this approach, pre-processing efficiently improves by more than 3,000 times. Another important optimization is mixed precision. We use reduced precision carefully. Selected variables are stored in reduced precision, such as FP16, to save memory and bandwidth. But the arithmetic operations are still performed in FP32. To make this practical, we use an automatic workflow based on auto RPE. And the workflow evaluates which variables can safely use reduced precision storage and then deploys the selected format. In this way, we improve performance while maintaining model stability and accuracy. Now, I will introduce the AI-enhanced atmospheric parameterization. And the GRIST atmospheric model integrates an AI-based full physics parameterization package called APS. And instead of replacing only one physical scheme, APS replaces the conventional physical parameterization package. This is important because subgrid processes interact with each other. If we replace them separately, we may break physical consistency. To improve stability and physical plausibility, APS uses unsupervised learning and RBF-based reconstruction. The predicted tendencies are constrained within the convex hull of learned basis tendencies. This helps avoid arbitrary extrapolation, and which is a common risk in neural networks. And the second AI component is in the ocean model Lichen. Here we focus on near inertial waves named NIWS. We introduce an AI-based NIW parameterization that provides physically constrained tendency updates. And the model uses residual MLP trained on 27 million samples from high-resolution simulation data. These samples cover 1 year at 3-hour intervals. The AI model learns both instantaneous forcing and latched responses without requiring costly long integration or explicit filtering during runtime. And the result is that our model can better reconstruct near inertial shear variability and vertical structure. So next part is about the experiment. We evaluated our model on 3 large-scale supercomputing systems. The first is Lanshan, an ARM-based CPU system. And each node has 2 LX2 processors. And each LX2 package contains 2 compute dies with over 300 cores in total, and 8 HBM stacks with high memory bandwidth. And the second is the China's new generation intelligent supercomputer. And this is a GPU system. Each node contains server processors and 8 accelerators. Each accelerator provides high bandwidth memory and strong performance for many precision styles, including FP64, 32, TP32, and FP16 or BF16. And the third one is the new Zheng and the Ocean Light. And these systems are these three systems are very different. Evaluating our model on all of them helps demonstrate performance portability. Now let us look at the simulation results. The 1 kilometer simulation captures fine-grained dynamical structure, including typhoon, tsunami, and topography-controlled winds along the Himalayas. Compared with ERA5, the 1 kilometer simulation shows more detailed land surface wind structures because ERA5 has a coarser resolution. For typhoon simulation, the fully coupled model also reduces spatial biases in wind fields compared with the standalone atmospheric version. And this shows the importance of atmospheric ocean coupling at kilometer scale. And the AI-enhanced full-physics atmospheric parameterization also performs well. It captures finer structural details near the typhoon center, especially the steep sea level pressure gradient. And for the ocean component, we test the AI-enhanced parameterization on Typhoon Karathan from September 29th to October 3rd in 2024. And parameterization improves post-typhoon mix layer deepening by representing NIW-driven vertical shear and entertainment. And next, I will summarize the performance results on Lanshan. The 1 kilometer atmospheric model reaches about 1.72 SYPD with over 42% strong scaling efficiency. And 1 kilometer ocean model reaches about 3.11 SYPD with 36% efficiency. And on the new Sunway, the 1 kilometer atmospheric model reaches 0.67 SYPD, and the ocean model reaches 1.05 SYPD, and the coupled 1 kilometer system reaches 0.33 SYPD. And weak scaling results on Lanshan are also encouraging. As atmospheric resolution increases from 100 kilometer to 1 kilometer, simulation speed decreases only slightly from 1.8 to 1.7 SYPD with 95% parallel efficiency at the finest resolution. And for the ocean component, as resolution increases from 6.6 kilometer to 1 kilometer, speed decreases from 3.8 to 3.1 SYPD, maintaining about 83% parallel efficiency. So here is the conclusion. Our AP3-ESM V2 is a next-generation kilometer-scale coupled Earth system model, and it enables global simulations at one resolution with high computational efficiency. And the first contribution is a breakthrough in kilometer-scale coupled modeling. And the second contribution is a new hybrid AI physics paradigm. And the third contribution is the co-design between modeling and supercomputing. And it has been conducted to 3 different China's Exa-Scale supercomputers systems. Okay, that's all. And thank you very much. Yeah.
Thank you very much. Very interesting talk. Are there any questions? We have one online, which is about the reduced precision. So vendors appear to be reducing the higher precision cores in GPUs. If so, will this impact your research?
Yeah, yeah. You mean the second system?
Well, in general, I think that most of the vendors are kind of going towards more half precision and lower as well on the GPUs, basically. And you now presented 16-bit performance, right?
Yeah, yeah, yeah.
So how much is it actually helping, I guess, reduce precision? And how much do you still need single or double precision in this?
Okay, okay. Yeah. Maybe I think this is auto paradigm. Yeah, you use I just mentioned the tools. You can use it to recognize which variables use low resolution and which variables use high resolution. Yeah, I think it can automatically to do this.
Yeah, I was very happy that you referred to auto RP.
Yeah.
Yeah, interesting. Daniel.
Hi, thanks for the talk. I have a question to the trained physics package you used for your simulation. I mean, probably I didn't understand properly, but you trained your physics on ERA 5? Is that?
No, we trained the model simulation results. Yeah.
Okay.
Yeah.
Can you say a few words how you trained that, or on which data set, or how you exactly trained the physics? I didn't understand that, I think.
Yeah, I think most of now AI-driven climate studies use ERA5, but ERA5 is a low resolution, I think, yeah. But if you want to train a high resolution climate model, you have to produce the data by your own model, yeah. So we first simulate the model to produce massive data and train it, and to using artificial intelligence to reduce the running times for the simulation. Yeah, but I think this will only use part of the parameterization. Yeah, it's not the whole model. Yeah.
Okay, right, now I understand. Thank you.
Thank you.
There's actually a question online which is related, which is about the AI kind of physics-constrained AI model and extreme events. Do you see any problems kind of having the constrained AI model inside for extreme events?
Yeah, I think it's really it's a very good question. Yeah, I think physics controlled. Not AI. Most of AI model cannot achieve this physics controlled. But I think the future architecture should part of our model use AI and part of our model use physics parts. And I think these two models may interactions each other, and so yeah.
Okay, thanks a lot. I don't see any other questions here. I hope the session convinced you that we have really made a lot of progress in kilometer-scale modeling, and that we can actually now really run those coupled simulations at like 1 year per day's throughput, which basically means that we can really make science on it, and now basically using also the Exa-Scale machines almost at their scale. So I think we've seen 3 fantastic talks. Let's thank Juepeng and all the other speakers again once more.
Thank you. Thank you very much.
And then I release you to the lunch break. Thank you.